In order to be effective at being able to work with conservative vector fields, we need to be able to find potential functions, and that's what we're going to look at in this video. In order to determine potential functions, we need to understand some general characteristics of potential functions. Potential functions share a characteristic with antiderivatives. That is, that they can be determined up to some arbitrary constant, but we often omit this constant unless it has some important physical significance in terms of our problem. There are several ways to find a potential function for a conservative vector field, and we're going to focus on one method here. Here's an example with two vector fields. I want to determine whether the vector fields are conservative on the specified region, and if they are, I want to determine the potential function. The first vector field I want to work with is the vector field given by a vector with components -y, -x in R2 space. The second vector field I want to work with, defined on R3 space, is a vector with components x cubed, 2y, and -z cubed. For the first case, my vector in R2 space, my components of my vector field are -y, -x. I'm going to first determine if this vector field is conservative. The partial derivative of f with respect to y is the partial derivative of -y with respect to y, and the partial derivative of g with respect to x is the partial derivative of -x with respect to x. This gives me -1 is equal to -1, and therefore my vector field is conservative. In my second case, I'm looking at a vector field in R3. This is a little bit more complicated. I'm looking to find out if the partial of f with respect to y is equal to the partial of g with respect to x, if the partial of f with respect to z is equal to the partial of h with respect to x, and if the partial of g with respect to z is equal to the partial of h with respect to y. The partial of f with respect to y is equal to 0, and so is the partial of g with respect to x. My partial of f with respect to z is equal to 0, which is also what my partial of h with respect to x is, and my partial of g with respect to z is equal to 0, which is equal to the partial of h with respect to y. In this case, my vector field is also conservative. So now I need to find the potential function. I'm going to first find the potential function for my vector field given by a vector with components -y, -x on R2. F is equal to del phi satisfies the conditions that the partial of phi with respect to x is equal to f of xy, which is equal to -y in this case, and the partial of phi with respect to y is equal to g of xy, which is equal to -x in this case. I'm going to integrate the partial of phi with respect to x with respect to x. This gives me phi of xy is equal to the integral of -y dx. This gives me -xy plus an arbitrary constant c of y. Now I differentiate my new expression phi of xy with respect to y. This means I take the derivative with respect to y of minus xy plus c of y. This gives me -x plus c prime of y. Phi of y is equal to g of xy, but I've just taken the derivative with respect to y of the function I found through integration. I got -x plus c prime of y. Comparing these two, I see that my c prime of y is equal to 0, which tells me that c of y is any real number. Since it's any real number, I'm going to let it be 0, and my potential function phi of xy is given by -xy. For my vector field defined by the vector components x cubed, 2y, and -z cubed, I know that my vector field f will be equal to del phi because my vector field is a conservative field, and that this relationship satisfies the conditions that my partial of phi with respect to x is equal to f of xyz, which in this case is equal to x cubed. My partial of phi with respect to y is equal to g of xyz, which in my vector field is equal to 2y. And my partial of phi with respect to z is equal to h of xyz, which in this case is -z cubed. I'm going to integrate the partial of phi with respect to x with respect to x. This gives me phi of xyz is equal to the integral of x cubed dx, which is equal to x to the fourth over 4 plus c of yz, which is my arbitrary constant of integration. Now we differentiate my phi of xy with respect to y. I get the partial of phi with respect to y is equal to d by dy of x to the fourth over 4 plus c of yz. The first term goes to 0 because I treat it as a constant, and what I'm left with is the partial of c with respect to y of yz is equal to g. This means that c sub y of yz is equal to 2y, and now I integrate that with respect to y. This means that my arbitrary constant c of yz is equal to the integral of 2y dy, which is equal to y squared plus a different arbitrary constant that is now a function of z only, and I'm going to call that d of z. This gives me phi of xyz is equal to x over 4 plus y squared plus this arbitrary constant that's possibly a function of z. What I need to do now is determine the new arbitrary constant by differentiating this latest expression for phi with respect to z, so that my partial of phi with respect to z is going to be equal to the derivative with respect to z of x to the fourth over 4 plus y squared plus d of z, and that is going to be equal to h. The first two terms are treated as constants. I'm left with just my derivative of d with respect to z of the function d of z, which is equal to negative z cubed. Now I integrate my d sub z of z with respect to z, and I get d of z is equal to the integral of negative z cubed dz, which gives me negative z to the fourth over 4 plus c. In this case, my c is a real number, so we're just going to let that constant be 0. And my potential function, phi of xyz, will be given by x to the fourth over 4 plus y squared minus z to the fourth over 4. So I have a procedure for finding potential functions in R3 because they can be a little bit tricky to navigate. If I suppose that my vector field is given by a vector with components f, g, h, and I assume that it is a conservative vector field, although it's always a good idea to check this, then if I want to find phi such that f is equal to del phi, we're going to follow 4 basic steps. First, we integrate my partial of phi with respect to x is equal to f with respect to x in order to obtain phi. This phi will include an arbitrary function that is in terms of my other two variables, c of yz. Next, I'm going to compute phi of y by differentiating the phi we just found in step 1 with respect to y. And I'm going to equate this to g in order to find the derivative of c with respect to y. Then I integrate that derivative of c with respect to y in order to get c of yz, which will include a new arbitrary constant d of z. This gives you phi in terms of this new arbitrary constant. And finally, I compute my partial derivative of phi with respect to z by differentiating the phi that I just constructed in step 3 with respect to z, equating that to h, and this will give me d of z. Now, one of the things you'll notice is I'm always starting with a partial of phi with respect to x, moving through the partial of phi with respect to y, to the partial of phi with respect to z. There's nothing sacred about this order. There may be times when it may be easier to start with one of my other partial derivatives. It doesn't hurt to do that. Just keep track of where you're starting and where you need to end up. So now you get to try it. Pause the video and determine whether the vector field f given by the vector components yz, xz, and xy is conservative on R3, and if it is, find the potential function phi of xyz. When you're ready, restart the video to check your understanding. So I first need to test to see if my vector field is conservative. The partial of f with respect to y is equal to z. This is also the partial of g with respect to x. The partial of f with respect to z is y, and the partial of h with respect to x is also y. The partial of g with respect to z is equal to x, and the partial of h with respect to y is also equal to x. This tells me that my vector field is conservative, which means that my partial of phi with respect to x will be equal to f of xyz, which in this case is just yz. My partial of phi with respect to y is equal to g of xyz, which in this vector field is xz. And my partial of phi with respect to z is equal to h of xyz, which in my vector field here is equal to xy. I'm going to integrate the first one, the partial of phi with respect to x, with respect to x. And this gives me phi of xyz is equal to the integral of yz dx, which gives me xyz plus an arbitrary constant in terms of y and z only, which I will denote as c of yz. Now I differentiate my phi of xyz with respect to y. And I get the partial of phi with respect to y is equal to d by dy of the quantity xyz plus c of yz, which is equal to xz plus the derivative of c with respect to y, and this is equal to g. I'm going to set those equal to each other. Xz plus the derivative of c with respect to y is equal to xz. This tells me that my derivative of c has to be 0, so that my arbitrary constant is in fact a real number constant, and I'm just going to let it be 0. This tells me that a potential function for my conservative vector field is given by phi of xyz is equal to x times y times z. This is how we can work with conservative vector fields. There are many applications that involve these kinds of fields. Be sure and let me know if you have any questions.